Hello everyone, my name is Jianjun Xu, and I'm a machine learning engineer in Keysight Technologies, Santa Rosa, California. The title of my presentation is Artificial Intelligence and Machine Learning for RF and Microwave Design, Practical Technologies for Present and Future Applications. The presentation will start with a very brief overview of artificial intelligence and the machine learning landscape, and then we will focus on artificial neural networks and provide several key examples of modern ANN applications to electronic device modeling, device characterization, and electronic behavior modeling to illustrate the substantial benefits and the generality of the present techniques. The summary will be given at the end of the presentation with a very brief discussion of the potential of AI/ML technologies to address and solve future challenging and important RF and microwave design problems. Artificial intelligence, AI, is a technique that enables a machine to mimic human behavior. Machine learning, ML, is an application of AI that allows a machine to extract knowledge from data and learn from it autonomously. There are three popular types of machine learnings, which are supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is a machine learning paradigm for problems where the available data consists of labeled examples, which means that each data point has the input X, called features, and the output Y, which are the associated labels. And the goal of supervised learning algorithm is to learn this function f that can map x to y using available xy information. Once this f function is learned, we can use it to predict new output y prime given new input x prime, which has never been used in the training. Supervised learning has been used for a wide range of applications, such as regression, image classification, face recognition, speech-to-text, and so on. Unsupervised learning is a type of a machine learning algorithm that learns patterns from untagged data or unlabeled data. So you can see here, there's no Y information, there's no labels, only features X. And this has been used for regrouping and clustering. Reinforcement learning is an area of machine learning concerned with how intelligent agents ought to take actions in an environment in order to maximize the notion of cumulative rewards. Reinforcement learning is very good at making decisions and has been used for a wide range of applications, such as gaming, stock trading, and self-driving cars. All those three types of machine learning techniques have been used for RF and microwave design problems. Today, I'm going to focus on the practical applications of supervised learning to RF and microwave design, where given input and output information, X and Y, the goal is to find the function f that is able to map X to Y. Artificial neural networks, ANN, is a perfect candidate to accomplish this goal. Artificial neural networks is a machine learning computational paradigm based on nervous system. It is inspired by the study of the ability of human brains to learn from observations and generalize by abstraction. One of its important applications is to automatically construct nonlinear relations between multiple inputs and outputs. For example, if we know the input information x1, x2, and x3, and the corresponding output information y, the ANN is able to figure out the most appropriate or best f function for you, which map x to y. This is a simple example of ANN structure, which has an input layer with input neurons, a hidden layer with hidden neurons, and output layer with output neurons. And the neurons are connected. Each connection has a weight associated with it. And if we collect all the weights together, we call them AA internal weights, represented by V and W here. The universal approximation theorem of neural network has proved that such simple structure can fit any nonlinear functions of many variables. The AA is very easy to train on scattered data, which means there's no additional requirement on the training data. And the model evaluation is very fast. And so here I'm going to show you how the neural network generates its output Y given input X. Given input X, the weighted and summed products are generated as the input to the hidden neurons. And the hidden neuron will generate its output Z using its activation function, such as hyperbolic tangent function or sigmoid function. And the final output Y is a linear combination of hidden neurons' output. So you can tell from the process that it is very straightforward and simple. That's why the AN evaluation is very fast. AN is infinitely differentiable and smooth, and the model can be easily linked to a circuit simulator, for example, using Verilog A format or Onyx format. The AN training or AN extraction is an automatic process of adjusting the internal weights to let the model's output match the training data. So there's no equation development needed, and there's no user-defined parameter extraction strategy needed here. Next, I will talk about some practical AN applications to electronic device modeling and device characterization. Active device models are very important for efficient computer-aided design of the RF and microwave circuits. And good device models are able to shorten the development time or design cycles of the circuit and further enable the design of the subsystem, system, and instrument. Here, I'm going to use an empirical-based model as an example to show you the conventional device modeling flow. An empirical-based model is composed of an equivalent circuit topology and the model constitutive relations. For example, those the equations for the nonlinear charge and the nonlinear current source, shown as here. This is nonlinear charge, and this is nonlinear current source. And those are the model parameters, which can be extracted using the measured DC and the bias-dependent S parameters. However, there are some drawbacks in the conventional device modeling flow. First of all, it is very expert-intensive and time-consuming. Well, you can tell that those such simple formulas are only for illustration, and for the real case, the formulation can be very complicated and may have hundreds of parameters. It may take a PhD several years to develop such model and several days to extract such model. It is technology dependent, which means it's very hard to maintain, and the parameter extraction or optimization may not always well posed, and you may never get good results. In order to overcome those limitations, artificial neural networks, or ANNs, are used to represent or replace those model constitutive relations, where W are the AN internal weights. The AN-based model is very general and accurate. It is easy to extract since it is an automatic training process. It is technology independent, which means it is easy to maintain since there is no prior knowledge assumed here. The model evaluation is very fast, which will speed up the circuit simulation. The AN-based model is infinitely differentiable and smooth, which is good for nonlinear simulations. The AN trainings of the nonlinear current source and the nonlinear charge are shown in this slide. For the nonlinear current source, the standard AN training is used, where the objective of the training is to adjust internal weights W to let the model's output match the measured data. And the model results are shown here, where the red circles are the data And the blue lines are the results from AN model. You can see that they match very well. For the nonlinear charges, the adjoint neural network training technique need to be used since we don't have any explicit charge data to train the model, so we cannot measure charge. The available information is the bias-dependent S parameters or Y parameters. And from the equations as shown here, you can tell that the bias-dependent Y parameters have the derivative information of the charge with respect to their inputs, the terminal voltages. Adjoint neural network technique allows the neural network to be constructed from its derivative information. And the objective of the training is to automatically adjust internal weights W to minimize the difference between model's derivative output and the training data. So after training, we're going to use the original neural network as the charge function, which has the integration effects on the derivative data. And this charge function extracted is shown here. ANN has been used to represent the model constitutive relations of a DynaFET model, which is dynamic FET model for GaN transistors. As shown here, all the nonlinear current sources and the nonlinear charges are represented by ANNs, which are able to model the detailed, general, multivariant coupling of many dynamic variables. For example, for this drain current source, AN models the nonlinear relation of the drain current versus instantaneous voltages, VGS, VDS, junction temperature, TJ, and two trap states for gate lag and drain lag respectively, and two average biases. The AN-based DynaFET model is very accurate and general. There are no additional assumptions, for example, backgating or virtual gate. And of course, we need richer data necessary to identify those complicated dynamics. And this is achieved by measuring the time domain waveforms of the device using Keysight nonlinear vector network analyzer. After the model is extracted, we're going to achieve a global model that can predict simultaneously DC and S parameters, large signal nonlinearities such as distortions, load pull, PAE, long-term memory effects, and there is no application-specific model tuning needed here. DynaFET was used to model a 0.5 micron gate length, 6 by 60, total 360 micron gate width, GaN HFET from Raytheon. The left plot shows the effective IV curves of DynaFET model versus signal power levels in a simulation. And clearly, we can see the knee walkout or current collapse due to trapping. Those two plots are the modeled and measured load pull contours. And fundamental frequency is 10 GHz with 12 volts and 54 milliamp as the bias, and input power is 24 dBm. The red circles are the measured data, and the blue lines are the simulated results using DynaFET model. And this plot is the maximum delivered power contour, and this plot is the power added efficiency contour, where modeled matches the measured very well in terms of both the value and the location. AN has been used for cryogenic CMOS modeling, which enables the circuit simulation for quantum control applications, as shown here. Cryogenic CMOS modeling is pretty challenging since CMOS device characteristics at cryogenic temperatures are very different from those at the room temperatures. For example, as shown in these two plots, which are ID versus VGS for different temperatures, the mobility is greater and subthreshold slope is steeper at cryogenic temperatures. The existing models and extraction procedures may not be effective. You may end up with unphysical model parameter values if you just try to fit the data, which can make the model ill-conditioned and fail to converge in the simulation. So far, there's not yet consensus on a standard CMOS model, although there are a lot of efforts. Here, in this work, AN is explored to automatically generate CMOS simulation models from measurements without requiring a physical-based compact model. And the modeling flow is shown here. Given the measured data, for example, the drain current at different biases for a wide range of temperatures, especially down to cryogenic temperatures, and for a wide range of device sizes, the AN model can be constructed or trained from those data. And after training, the trained model can be easily linked to a circuit simulator, such as Keysight ADS, for high-level circuit simulation and design. This slide shows the circuit validation results of the AN models. And those two circuits are voltage reference circuits. And those are the Keysight ADS implementations of the circuits using AN models. And here, we compare the measured performance and simulated performance. Qualitatively speaking, the results are pretty good, especially at low temperatures, where we can see that the simulated results can predict the subtle changes versus temperature, where the textbook equations cannot predict. AN has been used for battery modeling, which creates this dynamic nonlinear electrothermal model of the battery, where each component of this battery model is a nonlinear function of temperature and the state of charge, which is represented by AN. And this AN-based battery model can be used for emulation, prediction of the battery management system, parameter extraction and classification, electrochemical modeling, and other applications. The modeling flow is shown in this slide. Using Keysight battery test system, we can measure the electrochemical impedance spectroscopy of the battery, the EMS of the battery, at different temperatures and the state of charges, different SOCs, and which are plotted here, where it is in the format of the imaginary part of the impedance versus the real part of the impedance. And those information can be used to extract the component values of this battery model. All the component values are nonlinear functions of state of charge and temperature. As an example, for this component, R0, the extracted values of R0 versus temperature and SOC are plotted here, shown as the red dots here. And we need a nonlinear function that can map this R0 temperature SOC relation, so we can use it to predict R0 at other temperature and SOCs, which are not used in the model extraction. And of course, AN is the best candidate for this kind of task, which is able to find the nonlinear relations between input and output using available data. So we can easily train a function to learn this relation, and the trained results are shown as the surface here. Now we can use this surface OEN to predict R0 for any other SOC and temperatures. If we repeat this AN modeling procedure for all the components in this battery model, we're going to achieve an AN-based battery model that is able to predict the battery performance at all kinds of SOC and temperatures, shown as the blue lines here, where the red circles are the measured data, which covers only a few SOC and temperatures. So once we have this AN-based battery model, we can use it for emulation, prediction of the battery management system, parameter extraction classification, electrochemical modeling, and other applications. Next, we will introduce the hybrid physical AN modeling methodology, which combines the existing physical model with artificial neural network, AN, resulting in a hybrid model that maintains the existing physics with increased accuracy. As an example shown in this slide, this is a physical model of power MOSFET device, and the drain current source has the formulation shown here. And from this plot, we can tell that the existing physical model is not able to match the measured data very well. We notice that if one of the model parameters, transconductance Kp, is changed from a constant value, which is default for physical model, to a set of values which are optimized for every VGS to let ID match the data for that VGS, we can substantially improve the model accuracy, which will end up a nonlinear relation between the Kp and the VGS shown as the red circles here. But we don't have any explicit equation to describe this relation. But it is a very easy task for AN, which is very good at finding relations between input and output from the available data. So once we train AN to learn this nonlinear function, and we can put it back into the existing physical model, then we will obtain the hybrid physical AN model, which is able to improve the model accuracy substantially, and at the same time maintain all existing physics. For example, shown as the interpolation and extrapolation here. There are other ways to put constraints into AN to maintain certain required behavior. For example, we can modify the neural network structure. In this example, we want the AN to have cross-zero behavior, which means that when the input is equal to 0, the output should be 0. And we can easily find practical applications that require such constraint. For example, diode modeling. For a diode, when the voltage across the diode is 0, the current from the diode should be 0. Any diode model without this constraint will be quantitatively wrong and could have major consequences in some applications. And this cross-zero requirement can be easily added to the AN by adjusting its structure, as shown here. Because we have the path of input going through here and multiply the output of the neural network to generate the final output, we can guarantee that the output is 0 when the input is 0. The modeled result for the diode is shown here, which is the current versus voltage in log scale, where the red symbols are the measured data and the blue line is the result from the AN model, which has the constraint. We can see that not only the match is perfect, but also the cross-zero is maintained. This is another example of putting constraints into AN. In this example, we want our AN-based device model to be intrinsic drain source symmetric, as shown here, which means that the model is invariant with respect to the intrinsic drain source exchange. In other words, after switching the drain and the source, the current that goes into this port should be the same, and the current that goes into this port should be the same as well. And this is the requirement on the device model used for mixer and switch applications. After switching the drain and source, we need to define the voltage again. The original voltage, V, is defined as VDS and VGS. So VDS and VGS. The equivalent operating point called V hat is defined as minus VDS and VGD. And if we switch the drain and source again, we call it V hat and hat, and it will go back to V. Here, I'm not going to go through the detailed derivation of the current and the gate current and the drain current, which has the intrinsic resource symmetric, but I'm just going to give you the conclusion directly. Basically, in order to model the gate current and the drain current, we need a symmetric function, Fs, and the anti-symmetric Fas with respect to V and V hat. In order to address those requirements, AN with symmetry and anti-symmetry constraints are proposed. And this is the symmetric AN. You can tell that switching V and V hat won't change the value of the output of this network. And this is the anti-symmetric AN. And you can tell that if we switch V and V hat, the output of the network will have a sign change. The value won't change, but it will have a different opposite sign. So this is the anti-symmetric. And both of the networks can be trained using the data defined on half space. And the symmetry property or anti-symmetry property will guarantee its performance on the other half space. The modeled results are shown in this plot, where the AN-based ID model is trained using the data in this box, where excellent agreement is achieved, and the model is able to match the measured data in this validation domain in the other half space due to its built-in symmetry property. We have been talking about using AN for electronic device modeling. Next, let's talk about the practical AN applications to device characterization. In this example, AN is used for FET's thermal resistance extraction, or RTH extraction. RTH is a very important parameter of the device, which can be used, for example, for calculating device self-heating and for device reliability analysis. In this work, a methodology that combines the DC-only measurements and AN model is developed to estimate FET's thermal resistance, RTH. The idea is shown in this slide. This is the drain current and GM versus VGS plot. At very forward bias in a saturation region, for example, VGS equal to 1.2 volts, and GM is almost equal to 0, we can measure the drain current versus VDS at different ambient temperatures, as shown here. So this ambient temperature is going from low to high. And the basic assumption is that the device has the same junction temperature when the drain current values are the same. In other words, when you see the same drain current, you can assume the device has the same junction temperature. Based on this assumption and through the derivations here, we can come up with the formulation for RTH, shown here. Now, the key is to find the accurate differentiable function I, which is a nonlinear function of the drain current versus ambient temperature and VDS. Well, since we have the measured data available for this relation, we can just simply use AN to represent this I function. The RTH extraction flow is shown in this slide. First, we use the measured DC data at VGS equal to 1.2 volts with different ambient temperatures as the training data to train the neural network model, where this is the standard training. The objective is to automatically adjust interval with W to let the model's output match the measured data. After training, we will use the trained model and its corresponding adjunct neural network to generate the value of I, di dTA, and di dVDS. And those three values will be used in this formulation to calculate RTH. and the extracted RTH values through this formulation are plotted here, which is a very good estimation of thermal resistance with just simple DC measurements. Next, let's talk about using ANN for HBT's thermal resistance extraction, which is different from fast RTH extraction that I described in previous slides. For HBT device, the measurement is based on DC IC-VCE family of curves with forced IB, and we can plot VBE versus VCE with different IE for fixed ambient temperature. For this case, it's 57 degrees C. The idea is that when VCE is extrapolated to 0, linearly or quadratically, using the measured information here, there will be an interception point, shown as the green dot. Since VCE is equal to 0, there is no power dissipation, which means there's no self-heating in the device, so the device junction temperature Tj is equal to the ambient temperature. And for this case, Tj is equal to 57 degrees C. If we collect all the green dots, and we're going to have the information of VBE as a function of IE at fixed junction temperature, which is equal to 57 degrees C. And if we repeat the same kind of DC measurements at different ambient temperatures, and repeat the same extrapolation to VCE equal to 0 procedure, we can collect all the magenta dots, which have the information of VBE as a function of IE and Tj. And if we can find this function f, we can numerically solve Tj with VBE and IE as the inputs. So finding this f function is the key here. In this work, a knowledge-based neural network, KBNN, is proposed as the solution, which is able to automatically do quadratic extrapolation to VCE equal to 0 and find the f function that relate VBE, IE, and Tj. From its formulation or from its structure, we can see that the final output VBE is a quadratic function of VCE, which is the knowledge that we put into this KBNN. The three coefficients of this quadratic function versus VCE are all functions of IE and ambient temperature, which are represented by three ANNs: A-ANN, B-ANN, and C-ANN respectively. When VCE equal to 0, only the A-ANN is left, which corresponds to the magenta dots from quadratic extrapolation, and it is exactly the f function that we are looking for. The training of this knowledge-based neural network, KBNN, is shown here, where KBNN's weights, WA, WB, and WC are automatically adjusted to minimize the difference between the KBNN's output and the training data. Once the training is done, which means ANN, BANN, and CANN are determined, we can use the ANN to numerically solve Tj with IE and VBE as the inputs. And the extracted values of Tj are shown in these plots, and which can be used to calculate RTH, which is shown here. Next, I will talk about the practical ANN applications to electronic behavior modeling. Unlike device model, where we need to develop an equivalent circuit topology and the model constitutive relations, behavior model is like a black box model, which is used to model a circuit or system from its input and output information without relying on its internal details. The extracted behavior model can be plugged into a higher level circuit or system simulations, contributing to the increased design efficiency. The input-output information of the circuit or system for behavior modeling can be measured data from the real circuit or system, or the simulated data from the detailed circuit model or detailed system model, which corresponds to the measurement-based behavior model and the simulation-based behavior model. The measurement-based behavior model can be used in the situations that the circuit model may not exist, or the circuit models may be inaccurate, or we want to completely protect the design IP. The simulation-based behavior model can be used in the situations that the detailed circuit simulation is too slow, and we want to have a faster implementation. Or we want to design a system before building IC, which will help speed up the design cycle and reduce the time to market. Or we want to completely protect the design IP, where we don't want to share this detailed circuit design with other people. Or we want to do more in simulators than possible on instrument. In this talk, I'm going to present some examples of ANN-based behavior models, covering both frequency domain modeling and time domain modeling. For frequency domain behavior modeling, let's use AN-based X parameter as an example. X parameter defines the nonlinear time invariant spectrum maps between the incident, like A, and scattered, like B, complex phasors, or the maps between the A waves or B waves, in other words, that in principle completely specify the steady state large signal component behavior. And there are three types of X parameter functions here, specified by the superscript F, S, and T, respectively. Each X parameter function is evaluated at the large signal operating point, LSOP, defined by, for example, bias, frequency, input power levels, and loads. The F function models the device response assuming perfect match at the harmonic frequencies at each port. And S and T functions model the device first order sensitivities to mismatch at the harmonic frequencies. The existing X parameters are in the format of tables, which means the F, S, and T functions are represented by tables as shown here, and which has several limitations or problems. First of all, the graded data structure, the tables, forces high volume of data measurement. Some conditions are hard to measure and difficult to measure. For example, some conditions may damage the device. An accurate simulation requires a large table of data, and loading such large tables into simulator may take a long time and occupy a huge amount of memory. And the results may depend on particular simulator capabilities to read tables and interpolation algorithms. By replacing the tables with ANNs, we are able to avoid those limitations and have extra benefits, as shown here. For example, the data can be taken as needed for accuracy. So here we can use adaptive sampling to take the measurements, and as may be constrained by device operation. And since the discrete data is converted into ANN smooth functions, we can use the ANN-based X parameter model for future applications downstream. For example, optimization, system simulation, hierarchical modeling, and the digital twin. But we also want to mention one downside of ANNs for X parameter modeling, which is shown here. Since there are so many X parameter functions, for example, F function, S function, and T functions, to be represented by ANN, the training time may be long, and it will require a parallel training infrastructure, which is able to train multiple ANNs at the same time. A load-dependent AN-based X-parameter model was developed for a 1-watt commercial packaged HFET transistor. And this is an internal keyset example of replacing X-parameter tables with parallel trained ANNs, and it has not been published yet. This is the validation of comparing the measured and simulated load-pull contours of delivered power. And the blue lines are the measurements, and red lines are the simulated results from AN-based X-parameter model, where excellent agreement is achieved. And the measured and modeled time domain waveforms of the output voltage and current for two different loads, one load is here and one load is here, are compared, where the symbols are the measured data and the lines are the simulated results from AN-based X-parameter model. Again, excellent agreement is achieved. And this validation can also be plotted in the format of dynamic load lines, for example, current versus voltage, as shown here, and the match is perfect. For time domain behavior modeling, recurrent neural network, RNN, and the dynamic neural network, DNN, are good candidates. Basically, the model's output, YT, is not a static function of the input, xt. Instead, it is a nonlinear function of the input and the history of the inputs and outputs. And this history can be delays for recurrent neural network, which is defined in discrete time domain, and the derivatives for dynamic neural network, which is defined in continuous time domain. This example demonstrates the behavior modeling of a RFIC power amplifier through the recurrent neural network approach. So this is the original circuit, and this is the RN model. Testing is performed by comparing the RN model with the original amplifier with different set of signals never used in training. Here, the circles are the results from the original power amplifier, and the lines are the results from the RN model, and excellent agreement is achieved. This table compares the CPU time for evaluating 900 different set of input and output waveforms using RN model and the original amplifier, where definitely we can tell that the RN model simulates much faster than the detailed circuit model. This example demonstrates the behavior modeling of a mixer, a gain stage amplifier, and an output stage amplifier through dynamic neural network approach, or DNN approach. Then the three trained DNNs of mixer and amplifiers are combined into a DBS receiver subsystem. And this is the DNN version of the system, and this is the original system with detailed circuits. The overall DBS system solution using DNNs matches that of the original system as shown in this plot, even though such distorted signals were never used in training of any of the DNNs. Here, the circles are the results from the original system using the original detailed circuits, and the lines are the results from the DNN models. A further comparison is made between the DNN approach, the conventional static IQ neural network approach, and the conventional behavior modeling approach, where accuracy and computation speed with different methods for DBS system simulation are compared. It is observed that the DNN approach provides the best overall performance, being much faster than the original system simulation and much more accurate than both the conventional static IQ neural network approach and the conventional behavior modeling approach. Summary. Today, we reviewed some powerful and practical artificial intelligence and machine learning (AI/ML) technologies for applications in traditional RF and microwave design and beyond. We have focused on the supervised learning, more specifically artificial neural networks (ANN), and provided several key examples of modern ANN applications to electronic, electrothermal, and electrochemical device modeling, device characterization, and electronic behavior modeling in frequency and time domains. And those practical examples have illustrated the substantial benefits and the generality of the present techniques. Of course, there are other applications of using unsupervised learning and reinforcement learning in the area of RF and microwave design as well, which won't be covered in this talk, but I can list one or two examples for you. For example, unsupervised learning has been used for automatic circuit tuning, which automates the post-fabrication circuit tuning process. The training data set consists of input measurement vectors with no output labels and is clustered using unsupervised learning. And the generated clusters are efficiently labeled and directly utilized in circuit tuning by calculating the values of the tuning parameters. And reinforcement learning has been used for optimization and multiphysics, where its powerful decision-making property is able to help the exploration and exploitation for design problems with many variables. To summarize, artificial intelligence and machine learning is a very powerful tool that has been widely used in the area of RF and microwave design. It has a great potential to address and solve future challenging and important RF and microwave design problems. For example, AI/ML techniques are expected to help 6G networks make more optimized and adaptive data-driven decisions, alleviate communication challenges, and meet requirements from emerging services. Thank you very much for listening to this talk. All the references that are used in this talk are summarized in the next slide. Thank you.